Thanks for coming here, and this is our fourth edition of a masterclass. So the masterclass is founded by one of our alumni, called Lawrence Garenstrom. He's very kind to found this masterclass. Basically, the idea is like give a crash course on a certain topic on complex systems. So today we are very happy to have the expert on this field, the Professor Jean-Philippe Bouchaud. And before I give floor to Jean-Philippe, and I would like to introduce our Vice Director, Dak Pandya. And it's his effort to get Jean-Philippe here. And so I give floor to Dak to introduce Jean-Philippe.
Well, so yeah, we are extremely happy to have Jean-Philippe as the speaker for the masterclass today and tomorrow. I think, well, Jean-Philippe has made his career in statistical physics, and he was, as far as I remember, after getting into the field of statistical physics, he's been a star. He's also been my hero because we have overlapped on multiple things. I used to be in awe when he spoke about stochastic processes in general. That's basically his field. And 1993, he started to go into economic physics, right? Yeah, kind of found the field of economic physics, of combinations of economics and all kinds of stuff. I think he started market calculations, if I remember correctly, and then moved on to many other things. And then he joined CFM-Imperial. 94. 94. So 94, he joined the fund management, CFM. And since then, I think last time when I visited him, that was last September, I heard that he was, he's the boss of the company and kind of overseeing something like 150 people. Okay, let me get that. This is what I heard. I didn't directly ask him, but he keeps a constant presence between science and managing the company. And yeah, I think more than that I cannot really say.
Okay. So CFM is a 320 people company. Okay. But we are 5 in the board, so I'm sharing the load with 4 other people, which is very, very, very useful. I'm more concerned with the research part of the activity and not the rest. Okay, well, thank you very much for having me, and I'm happy to give these 3 lectures on complex systems, and so more specifically collective effects and crises in socioeconomic systems. And so I'll give you 3 different views on that broad topic. Of course, one has to choose, and there's many, many things to talk about. So I'll try to remain at the high level during the lectures, and so I've understood that there are also hands-on sessions later, so we can go deeper into mathematics and details and how to do some of the calculations. So this is what goes later, but of course you can interrupt at any point. So my first topic today will be about random multiplicative growth, and you will see that it's a very interesting, very natural also, and very rich framework to describe many things that take place in complex systems. So as a way of introduction, let me speak about parallel distributions. So why this is important is because we want to speak about crises, and crises, they are very rare in the sense that if they were not rare, they wouldn't be called crisis, they would be just normal state of affairs. But they are not that rare either, because otherwise we would never see them. So they have to be kind of in between rare and not rare. And the natural framework to describe this type of phenomenon, that for which rare events are not that rare, are distributions that decay as power laws. So this is the power law I'm speaking about. This is the cumulative, this is my notation for the probability of being larger than. So this is the cumulative distribution, or the complementary cumulative distribution for observing a certain value x. And when x becomes large, it decays as some amplitude c divided by x to some power mu. So mu is the exponent. And as mu increases, the decay gets faster and faster. And as mu decreases, the decay gets slower and slower. So if you want flatter tail corresponds to smaller mu. And so what's interesting is that a lot of phenomena, in particular in socioeconomic contexts, seem to be behaving as parallels in the tail. So maybe the most well-known and most ancient is due to Pareto in the beginning of the 20th century. So this is the distribution of wealth, and it's surprisingly robust. I mean, so Pareto reported this, as I said, in the beginning of the 20th century, and already noted that this law for the distribution of wealth seemed to be pretty independent of the country it was looking at. And so it's really interesting to read what he was saying at the time, and he was already thinking about a kind of universal mechanism. So for wealth, mu, this exponent here is around 1.5. And you know, if you want to have to be convinced that this is real, that the power law really describes something real, let's think of these numbers. In 2005, it has changed since then, but these are the numbers I remember. 7 million people on the planet were reported to have a net wealth larger than $1 million. Okay, so if you use this power law distribution here with an exponent 1.5, that is 3/2, it means that every time you multiply x by 100, 100 is 10 to the 2, you divide the probability of observing that number by 1,000. This 1,000 is 100 to the power 3/2. So let's look. If I multiply 1 million by 100 and 100 again, I get 10 billion. And so I should divide 7 million by 1,000 and 1,000 again. And this leads me to 7. And indeed, in 2005, there were a handful of individuals with a net worth larger than $10 billion. So it's really striking that this simple law captures something, you know, which means that you change the wealth by 4 orders of magnitude, and you're still more or less along this distribution. So it must mean something, even if you don't believe that mu is the same for every country or every epoch, and actually one can detect changes of mu. Maybe you've heard that in the US right now, inequality has become larger than in any time in history. It's reported to be larger than Russia before the revolution, or even France before 1789. So it's really striking inequalities of wealth in the US right now. So probably mu changes a little bit, and we'll see why it could change. But you know that it is a broad distribution like a power law, and not an exponential or a Gaussian, something that is very quickly is beyond any doubt. So there are many of these power laws reported in the literature. 2 famous ones that go under the name of zip law. When mu is equal to 1, this is a special case that people call zip. Here is a famous one, which is the distribution of city sizes. And so this is a log-log side. I haven't specified this because it's so natural to me that I forget to specify. These are log-log plots. So in log-log, the power law looks like a straight line, and the slope is mu. So this is the distribution of city sizes, and mu equal 1. And this is the distribution of firm sizes in the US in 2000. And again, mu is 1. So firm sizes, again, you see it's striking number of employees. That is the particular measure of firm size goes from, well, that's 1. So it's hardly a company, but you know, from 5 to 10 to the 6. Walmart is around 1 million employees. You see this very beautiful power distribution with exponent 1. Okay, and then there are various other, I've listed a few here, like the cost of industrial disasters seems to be around 1, maybe because of the firm size, I don't know. Book sales, 2.5, box office, 1.6, and so on and so forth. There's a huge list of more or less arguable power laws, but at least this is a very important framework. So let's look at particular values of mu. When mu is greater than 2, then you can show that the variance of the distribution, and hence also its mean, is finite, mathematically finite, you can compute it. And therefore, when you start adding these random variables, for example, adding the wealth of people to count the total wealth in a population, then the sum converges to a Gaussian. This is the central limit theorem. And nothing much happens, except that if you go into the details, there are subtleties, but let's get them for the moment. When mu is between 1 and 2, then the mean is finite, but there's infinite variance. And when mu is less or equal to 1, then there's mathematically infinite mean and infinite variance. And then in these cases, we go into another type of central limit theorem, which is called the Levy-stable central limit theorem. And again, I won't go into the details. What you should remember is that as soon as mu is less than 2, then the largest events, even if they're rare, they dominate observation. So for example, this is a representation of this, a visual representation of this dominance of extreme. This is the sum of random displacement of finite mean and finite variance. And so the central limit theorem here appears like the Brownian motion of this particle undergoing these little changes of position of finite mean and finite variance. But as soon as mu is less than 2, the visual picture is completely different. You see, this is called a Levy flight. So the distribution of jump lengths is a power law with mu less than 2. And what you see is that the motion now is made of little steps and then a very big one and so on. And what's interesting is that the scale of this graph is actually dominated by the largest jump. So here the largest jump you see visually is like 2/3 of the total extension of the walk. And this is true on all scales. That is, if I were to continue this flight, or if I zoom in a subpart, you see that it's always true. It's always true that the whole sum is dominated by only a few events. And we'll make that clearer in a sense. You had a question.
No, I think you already defined it. But how do you define dominance? And it's probably, let's say, more than 50%.
It's scaling back. I'll specify it. Here is just visual, but I'll give a precise definition of dominance in a second. Okay, so what I want to talk about today is the mechanism leading to this power law distribution, which is very natural in many of the contexts that we've seen, which is multiplicative growth and random multiplicative growth. So I'm going to look at items. So I is going to label the item, and I is going to go from 1 to capital N. And each item has an equation of motion, if you want, a growth equation, which says that its change of size between t and t plus dt is proportional to its size, so it's multiplicative in that sense, times something that is going to be a random variable, eta I of t. I'll specify eta I of t in a second, but you can think of zi, for example, of the population size of city I, okay? And then, of course, the more people, the more children, and the more children, the faster the growth of the population, and so on. But it could be the growth of a species in an ecology, or a mutant virus in the case of COVID, as we've heard. And in socioeconomic context, Zi can be the wealth of agent I. So this, as you invest, usually there's what's called the rate of return. So the rate of return means that the wealth growth is proportional to wealth itself. In a sense, this is the essence of capitalism. It could be, if you have a portfolio, then Zi could be the amount that in your portfolio you then invested in asset I. So I would be the list of the assets in your portfolio, and each of them grows like this. But it could also be the size of the firm I. So the larger the firm, maybe it's going to hire more employees because every department is going to need more employees and so on. So you see that it's a very generic type of phenomenon. And many, many examples beyond these ones are available. So let me specify a little more what I mean by eta I of t. One has to specify its mean. So I'm going to assume that the mean is 0. This can also, it can always be kind of removed by removing the average growth rate of everybody. But of course, maybe the mean is different for different i's. And so in general, I'll call MI the mean growth of species I or city I. And then the covariance of these etas is delta ij, meaning that the growth rate is independent from I to, oops.
Broadcast. Was what to join online the course.
If I pay for attention,
So I'm assuming here that different cities grow with independent growth rates, or at least decorrelated growth rates, which can be debated, but that's the simplest framework. And then, as a function of time, this is going to have some persistence time, which means, again, if you think of growth rate of a city, it's going to be favored for a while. You know, the economic conditions or health conditions will be favored for a while, which means that instantaneously eta I is going to be larger than usual, larger than zero, the favorable growth. And then after a while, the situation will revert and it's going to be lower than zero. So this is a simple correlation function for this noise, meaning that favorable and unfavorable conditions alternate with a typical time tau, which I call the persistence time here. And the amplitude of these fluctuations is captured by this number sigma squared, which means tells you how much this growth rate is varying from year to year. So imagine, I don't know, for example, investment. Investment, it's reasonable to think that some investment make plus 10 or plus 20% a year. Others make you lose 10 or 20% a year. So sigma in this case would be around 10% a year, for example. Yes?
So I was just wanting to double check it. So E is expected value or?
E is expected value.
Yeah.
Yes.
Just wanted to make
Sorry.
sure.
Yeah. I mean, it's true that depending on communities, people tend to have different notations for this thing. It seems that most people, I mean, physicists tend to use brackets or over bar, and that's what I was using for a long time before realizing that apart from physicists, everybody else uses these notations, expectations. Sorry, yes.
No.
Yeah, sure.
And the mu t represents what? The n t.
Eta is the growth rate.
Okay.
Eta is the growth rate. It's the fluctuating part of the growth rate.
Okay.
So that's what I was saying. So imagine that on average eta is 0, but then some years the growth rate is plus 10%, other years it's minus 10%. Then sigma squared would be 10% squared, that is 0.01.
And so when you say eta t and eta t dash, what's the t dash?
It's another time. For two different times, the correlation between the growth rate at time t and at time t prime. If t equals t prime, it's sigma squared over 2 tau. But if t is very different from t prime, if t and t prime are very far away, then it's 0. Then these fluctuations become decorrelated when t and t prime are far away from one another.
Thank you.
Sure.
And if you say the expectation of eta I is 0, but for every mi it lies differently, are you then sort of normalizing differently towards the center for every
So
everything differently?
Yes. So indeed, this is consistent with this notation. If I had an mi for each I, then I would have to remove mi squared. That is, it's really this product of eta I, eta j should be corrected by mi and j. So it's really in the case where the mean is 0, then the second moment is equal to the parents.
One more small.
Sure.
Sorry. Why are there I and J? Is it
because I have a lot of cities, so some
okay,
so there are
it's different cities.
Different cities, yes.
Okay.
I is one city, J is another city, or maybe the same city. And actually, the only case where this is non-zero is when you're looking at the same city with itself. Because as soon as you're looking at two different cities, then you assume that they're growing at different rates. So this will be the model I'm looking at, but let's go a little deeper now into this question of dominance of extremes. Okay, so in particular, I'm going to be concerned with the phenomenon of concentration or condensation, depending on the field or what you want to describe. So the question is, again, coming back to my little drawings earlier, is the total wealth in the hands of a few individuals, or is the total wealth kind of distributed? Or is the whole population of a country concentrated in a single city, or is it spread out in a lot of different cities? So these questions of inequality measures or concentration measures have a long history, in particular in economics. And so there are many indicators for inequality, but two are well known. One is called the Gini coefficient, and the other one is called the Herfindahl index. And so let me go through quickly these two. So the Gini coefficient is constructed as graphically like this. So here you rank people from the poorest to the richest, okay? And here you sum the corresponding total wealth in the hand of the first 20% people, 60% people, 100% people. So obviously when you start at 0, then there's no wealth at all. And when you end at 100%, then you've counted the whole wealth of the nation. But then if people were actually equal in terms of their wealth, and as soon as you add one more individual, you add the same amount of wealth. And so you would have a straight line across the diagonal. But of course, if the poor are very poor, at the beginning, you're not adding much, and at the end, you're adding a lot. So you're having a curve here that is very convex like this. And so the Gini index is the area between this Lorentz curve, so-called, and the diagonal, A, divided by A. So you see that if you're in a perfectly equal world, then in Gini index is 0 because the area of A is 0. But if you're in a completely unequal world, that is, everybody has nothing except one person who has the whole wealth, then you would have a line that goes completely horizontal here and then jumps to 1 at the end. And in this case, the Gini index would be 1. Okay. So that's one measure. Another measure that also appears in physics in many contexts is the so-called Herfindahl index, H. And so let me define H from, first of all, the weights. So Wi is going to be Zi divided by the sum of the Zi. So if you think about countries and cities, Zi is the size, the population size of city I. KZ is the sum over all cities of the population, so it's the populations of the whole country. And Wi is therefore the weight of a city in the population of the country. So by definition, if you sum the Wi, you get 1. And the sum of the weights is 1. But if you sum the weights squared, you get something interesting. Why? Well, imagine that you have n cities and they're all equally populated. Then Wi would be 1 over n. Wi squared would be 1 over n squared. And therefore the sum over 1 over n of 1 over I of 1 over n squared would be 1 over n. So for large n, h would be 0, which goes to 0. On the other hand, if one city has a weight of 50% and all the rest has whatever, then you know that h, because it's a sum of squares, is at least equal to 1/2 squared, which is 1/4. So whatever happens to other cities, you know that h is not going to go to 0 when n goes to infinity. So this distinguishes cases where there's condensation, that is, a finite fraction of the population or of the wealth is held by a few cities or a few individuals. And when h goes to 0, it means that it's equally spread out, I mean, more or less equally spread. So let's look at what happens for these parallel distributions that I've talked about at the beginning. Well, h, when mu is greater than 2, you remember mu greater than 2 means that there's finite mean and variance. Then we're in the equal case, or more or less equal case, where h goes to 0 is 1 over n. So if you sum random variables with the distribution like this, that falls off fast enough, then you'll be in an equal society. If mu is between 1 and 2, it still goes to 0, but with a strange exponent. Let me not get into the details of that. But what's interesting and really answers your question in a very precise manner is that as soon as mu is less than 1, then h is n to the power 0. That is, it doesn't decay when n increases. And therefore, it means that, for n very, very large, even when n is very, very large, there are a few events that capture the whole phenomenon. So this is really this picture here that is true on all scales. Okay, so that's natural to call these phenomena when you have dominance of a few extreme concentration, because the phenomenon concentrated when you have a few people or concentrated in a few cities and so on. The Gini coefficient, an approximate formula for the Gini coefficient for this distribution is 1 divided by 2 mu minus 1. So you see that when mu increases, inequalities disappear. And when mu reaches 1, 2 minus 1 is 1. So 1 over 1 is 1 again. And of course, the Gini can't be greater than 1. So it's another way to see that you have concentration at the point mu equal 1. And as I've emphasized, it's funny to see that many phenomena seem to be described by the marginal case, mu equal 1. This is the set distribution, as I've said. For example, if you think about cities and thumb sizes, you're exactly at this point where you go from non-concentrated to concentrated, just at the boundary between these two regimes. Okay, so endowed with these measures of inequality, let's look at what's going on for the random multiplicative growth model, and in particular think about what type of concentration phenomenon can take place. So again, this is my growth rate formula or equation of motion, and of course you can solve this immediately by going to logs. Zi over dt is e log zi over dt. It's just eta I of t, and the sum over time, the integral over time of eta I of t, because eta I tends to have positive and negative sign as time goes on. Then what you know is that for large enough times, when t is greater than the persistence sign, then the sum of these etas will be a Gaussian random variable of root mean square sigma square root of t. So zi will be of the form exponential of a random variable with a scale sigma square root of t. So that's, if you have individuals growing randomly, then some of them will be very small because psi I will be negative, and some of them will be very large because accidentally the psi I will be positive. And as t increases, the big ones will be bigger and the small ones will be smaller. So what happens if I sum over I these zi's? So again, this is a very naive model for growth of cities or wealth. And if I sum over I get the total wealth or the total population, and I can ask questions about inequalities, Findel. And what's interesting, and we'll see this in the hands-on session later, is that even the simplest model has a condensation transition as a function of time. And that's what I've shown here. So this is time. So you start with everybody with the same, every city with the same population, everybody with the same wealth. You let this equation of motion act. And then you look at the Huffield index as a function of time. And what you see is that for a while, the concentration index is going to be 0, which means that it's still well distributed. But then after the critical time TC, that I'm going to tell you what it is in a second, then strong inequalities in the sense of the Huffield index start to kick in. And you have a Huffield index that grows like this. And as time goes to infinity, the Huffield index will reach 1. That is, at very, very large time, you will be in the most extreme situation where everybody has 0 wealth and only a unique individual has a lot of wealth. So more precisely, the Huffield index is given by 1 minus mu. And I'm here using the same notation mu for a reason, a deep reason, is that behind all this theory, there would be a parallel distribution of exponent mu, but I don't want to go into that now. We'll see that later. And this exponent mu is square root of 2 log n. Again, log n is the number of cities or the number of individuals divided by sigma squared t. So this formula is only true when mu is less than 1, so that the Huffield index is 0 when it's larger than 1 and non-zero when mu is less than 1. And so you see that as the population size gets larger, mu is larger, so it's more difficult to have compensation for large population size. But after a certain time, if you fix n and wait long enough, then mu will certainly become less than 1. And so you have this condensation transition. If you have randomly growing objects, at one point, there will be condensation in a few of them. So there are 2 remarks here that I want to add to this, is that in this model, if you look at the global growth rate, so remember this curly Z here is just the sum, oops. Curly Z is just the sum, the total population or the total wealth. So it's very natural to ask what happens to the total population or total wealth at long times. And what you can show is that in this case, where there's nothing else than random growth rates with a mean 0 for each eta I, then the total population doesn't grow exponentially with time. It is the log of z divided by t equals to 0. So the global growth rate, if you want, defined by this, is still 0. I'm emphasizing this because you'll see how this changes in a non-intuitive way. This is going to be different as soon as I'm going to introduce an extra item to the model, which is redistribution. So I'll get to that. And second, even if there's condensation, I mean, it's not completely doomed for everybody, this model, because the rich guys after time t, the ones that dominate wealth or the cities that dominate the country, in this model, they have nothing special. And so if you wait long enough, they're going to be replaced by someone else. So it is true that as soon as t is greater than tc, as soon as you're in this regime here, you have dominance of a few extremes, but the extremes are not going to be the same as you wait longer. They're going to get replaced. of course, this is going to take a long time. And the rule of thumb, that's what I call aging, because some physical systems reveal the same phenomenon, is that the longer you wait, the longer it will take for the rich to become poor and the poor to become rich again. So there is this possibility of revival of the poor, if you want, but in this model, if you wait long enough, it's going to happen slower and slower.
Jean-Philippe, this is maybe you could give us a bit more intuition behind this, how this works. This is something I do not see through.
So the idea is here, Zi is exponential of psi I, and this psi I here is going to also evolve with time. So this is a kind of, hiding under the rug, the fact that this psi I at time t is a Gaussian random variable, but it's not time independent. So this is just a scale after time t, but one I has a negative psi I at some t, and then later on it's going to be a positive for random reason. Okay, so you remember that here I've assumed that everybody grows at the same average rate. So you have condensation. Again, this is a very important remark, is that I've given the same chance to everybody. I'm just finishing and then you see, I'm not favoring anybody in this model because everybody has the same average growth rate, 0, and the same fluctuations. But still, in this model, there is condensation after a time tc. Now, of course, I could start the model where I favor some individuals or favor some cities and disfavor other cities. So if I take mi to be different from I to j's, then of course I expect that I'm not sure this is describing what happens in the real world, but if you think of mi as a measure of smartness for individuals, then maybe some people are smarter and they get richer because they're smarter. I'm not sure that's true, but but let's make a kind of short cuts to the mechanism and think of that as a measure of smartness. Or in the case of cities, maybe some cities for geographical reasons are better meant for life, and so they're going to grow at a faster rate than others. And so I haven't answered your question. I just want to finish this. So of course, when you have different MIs, you expect condensation to happen even more. And that's what you find. That you find that the same transition, the same type of transition happens, it just happens sooner. It happens sooner in time because of this heterogeneity, this true heterogeneity of the population. And not surprisingly, in this case, it is the fastest growing, it's the largest MI that condensate wealth. And so in this case, there's no possibility for the poor guys to catch up because the average growth rate is different. Or in the city case, larger cities will continue to grow at a faster rate. So of course, they will gather the population. Note here that there's no saturation effect. In a city, you expect that this growth rate equation would at some point saturate because of steric effect. It's not possible to put an infinite number of people in a single city. Mm-hmm. Yes, so sorry, now
yeah, you got a formula with a C, was it the slide back? You asked about intuition. Do I get it right that at some point wealth is, let's say, big enough to buffer you against negative C?
So as I said, C is a shorthand notation that hides many things. Yeah. And the figure psi is actually dependent on time still.
Yeah, but
it becomes of order 1, but it depends on time. Mm-hmm. And it is positive for the richest guys at some time, but if you wait longer, it's going to get negative again.
Yeah, but you mentioned that over time, wealth or whatever you measure becomes more sticky in the sense that you're less likely to drop later on in time.
Yes.
And is that because we have more buffer robustness against negative
let me draw psi sigma squared of p as a function of t for a given I. This is t. This is psi I sigma square root of p. And so I'm fixing I here, looking at given interval. Yeah. And what you'll find is that this is a random walk, because this is the integral of a noise. So it looks a little like this. Yeah. And so you see that as you wait longer, it's going to take longer to get back. It's not a question of buffer. Really. I mean, you can think of that as buffer, but it's just a random walk. If you wait longer, a random walk will take longer to get back.
But I see it somewhat as a buffer. You accumulate some surplus, and it takes longer time to get rid of it.
Right. Yeah, you can think of that.
But it works the other way around. You've accumulated enough of foreignness.
Yeah, same thing.
Yeah. Same here. If you're in the negative, on the negative side, it's going to take longer to. Yeah. And you can actually compute precisely the correlation function of that noise and see that it depends. That it's not time translation invariant, that it ages in the sense that the time you need to get back is proportional to the time you've waited.
But if you would add in some extreme events.
Yeah. So yes, so I've actually removed my third note here because I didn't want to be, burdening you with remarks. Is that actually here I'm assuming that eta has no jumps. Eta is a well-defined object, but without these Powell distribution and shocks and so on. If you introduce some shocks at the level of eta, then something different happens. And I don't want to enter that right now. Okay, so fine, this is the kind of setting of the model. Now, what I want to look at is redistribution effects. And I want to see whether redistribution, in ways I'm going to explain, affects compensation and inequalities and the global growth rate. So at this point, we have a model with no redistribution. Every person grows its wealth at its own rate. Every city grows its population at its own rate, but they're independent. They're doing their own stuff independently from one another. And the only reason you have compensation is because you sum. The only way these I's and J's talk to each other is through this sum here. But the sum is not an interaction. The sum is just a mathematical description of what's going on. There's no interaction between individuals and there's no interaction between cities. But in reality, of course, there is interactions. For example, if you think about cities, some cities grow, but people move from one city to another. There's migration. So what happens in city I depends on the growth rate of city I, but also of the population that comes from other cities or that goes to other cities. So this introduces some redistribution. And in the case of wealth, well, there's redistribution also in the sense, for example, of taxes or of trades, of all sorts of interaction between individuals, which transfers part of the wealth from one individual to another. And so how does that affect condensation? You would think naively that it's going to reduce condensation because as soon as you spread things around, condensation is impeded. And the other question is, how does redistribution affect growth rate? And again, what is it doing? It's going in the wrong direction. So remember here, I've noted that in this model with the independent people, the asymptotic growth rate is 0. And I want to know whether the mere fact of spreading things around is going to affect this conclusion. And the answer is going to be yes, surprisingly. Even if all cities grow with a 0 average growth rate, the fact of moving people around will allow the population to grow at a finite growth rate, which is very non-intuitive at first. Okay, so let me put that in a mathematical framework. So dzi dt equals eta I zi. This is my previous model. Okay, so you've seen that before. But now I'm adding terms that describe redistribution. So this term here says that people in city J, they have some probability per unit time Jij to move from J to I. So this comes with a plus sign because the city I is going to grow thanks to migration towards city I from all other cities. And then there's inverse migration, if you want, people leaving city I. So this is with rate Ji, and this is proportional to the number of individuals in I. And this comes with a minus sign because people are leaving the city I. So this is random growth, and these are, exchanges or flows or migration or whatever you want to call it, depending on the context. And I'm going to call J the scale of these exchanges. Although in principle J is going to depend on Ij and so on. J will be a kind of generic term to describe exchanges. Okay, yes?
Then the immigration is not related to the size of the receiving city.
No.
So
in this model, the only way you're moving is because of your initial, but you could have some dependence of I on Jij.
Yeah.
You could say, I'm going to say that I, because it's big, is more attractive than J. But to keep it simple, I'm just adding Jij without specifying the structure of Jij. So this is explaining essentially what I'm just said. It's n cities or n people, population Zi, between T and T plus ET, a fraction Jij population I decides to move to city J. And then this term here is between T and T plus ET, population grows or dies with a random net growth rate that describes idiosyncrasies. And I've said that already, economic, health, food, culture, this all is included in this eta I of T. For in the case of city growth, in the case of individuals, it could be, as I said, access to information, smartness, whatever. Yes?
Eta I of T doesn't take into account the parameters of city J.
No, because this is only reflecting what's happening in city I. So everything that comes from city J is here, and apart from that, it's the previous model. But so, you can think of the same model in terms of wealth redistribution. So for example, taxes could be described that way. You're taking the wealth tax in particular, you're taking a fraction of the wealth of individual I, and you're redistributing to other people. You can give your money to charities and so on. Portfolio, I've said that ZIs could be thought of as the amount of money that you invest in asset I, but then as a function of time, people do what's called portfolio rebalancing. So they take part of the gains they've made in investing in I and redistribute their gains elsewhere in the portfolio. So this could be thought of, the very standard way portfolio managers handle profits and losses by redistributing the capital between different assets. But it could be also gene mutation, for example. If you think of I as a specific gene describing a virus, then growth rate of a virus could be modeled like a random stochastic process. But then there are mutations between different types of viruses that you could model like this. Yes?
Can I ask one question? Yeah, so
Sure.
I was just thinking, right, the fact that J is in this model not dependent, could you equate that to, so I'm always thinking of investors, that they actually use different strategies to determine what they're going to do? The fact that J is not dependent on...
J here, at this point, it could be anything. It could be dependent on I and J,
Yeah.
the way you want.
But because in this model you say we assume that there is no dependency on, let's take the situation of the city, right?
Yes.
We're not assuming that people want to move to bigger cities in the particular
You
models.
could.
Well, we
You
could,
could.
but we're not doing it.
We're not doing it right now. We want to have a kind of generic model to see what happens.
Yeah, and so the fact that we're using a generic model is that the equivalent to people using different strategies.
Well, I think strategies in the case of portfolio investment would be the I's and the J's themselves.
Yeah, exactly.
But not the assets. So,
okay.
So you can think of that as portfolio rebalancing in your universe of assets or portfolio rebalancing in your universe of strategies. So for example, you know, I don't know, I could be trend following or mean reversion or fundamental trading or whatever. And then you have this set of strategies in front of you and you decide to rebalance between them. That's perfectly viable too. And by the way, if you know, because you asked the question, if portfolio managers don't rebalance, then they will be faced to the concentration problem.
Exactly.
Then after a while, your whole portfolio will be in the best
strategy.
In the best strategy so far. You know, maybe there's no reason for it to be the best strategy, but you'll be kind of, you know, very ill-balanced because the whole portfolio will have condensed in the best performing strategy.
And you see no growth overall.
You see no growth overall. And later on, your best contributing strategy will happen to lose money. That's this graph here.
Yeah.
And so you don't want to do that. People don't want to have their whole holdings concentrating in a few strategies or a few assets.
Smart.
And J is probably not symmetric.
J is not symmetric.
It can be matrix from depending on whatever.
Absolutely, sure.
Every dot in the matrix can be a complex function.
Yes, yes, and even so that's why this is a huge model, because you can add all sorts of complexities in the JIJs. They can be non-symmetric. They can be time dependent. They can be Z dependent. That was the question earlier. So, this is a huge model, and people have only scratched the surface of this generic model. But I'm going to give you what happens in the simplest case already. But then, to your heart's content, you can
I can go loose.
Right. Okay, I don't know how many people are interested by the physics part of that, but I'm just flashing this very quickly without going into the details, because it turns out that this equation here, if you put it on a lattice and so if I and j become spatial positions, and you take the continuum limit, then this equation becomes what's called the parabolic Anderson equation. So dz dt equals the Laplacian of z. Now I is replaced by r, position, and the exchange gives rise to Laplacian, and then this random growth rate. So this is a very famous equation in physics, and in particular, it describes objects like vortex dislocations or polymers in a random environment. So these objects can be pinned by impurities, and there's a mapping between the statistical mechanics of these objects pinned by impurities and this equation, and therefore the problem of well condensation. And it so happens that in physics, it's the condensation transition is very important because it distinguishes a phase where this object here is pinned by impurities from a phase where it's free flowing. So if just a very quick remark, because I like this story a lot. In superconductors, magnetic field penetrates superconductors in the forms of vortices. But if the vortices are free to flow around, then you lose the superconducting property of the material. It dissipates energy when you flow current. So you've lost the miraculous property of superconductivity. If these vortices are free to flow, then there's no use to them. So, if you want to use superconductors, you should pin these vortices. And it means that you should prevent them from flowing. And it turns out that the transition from free flow to pinning is exactly the same mathematically as the transition from non-condensed to condensed in the wealth language. So I'm just saying this very quickly, but I'll skip that. Okay. So what are the generic results here? So as we just said, Jij can be complicated things and so on, but I'm going to dump everything in a single parameter, which I'm going to call J. So what are the generic results from this model? Well, first of all, I'm going to define now the asymptotic global growth rate. So again, the log of the population size, the total population size. So imagine that the population size grows like exponential of CT, then C is the growth rate, the asymptotic growth rate. I take the log and divide by G, then this is my definition of C. C is the average growth rate. And as I said, in the previous model, without redistribution, I told you C is 0. And so when all these cities, the growth rate of all these cities is 0, like in the previous case, you may naively think that redistribution doesn't change anything, right? I mean, cities were growing at a 0 growth rate, which meant, on average, that the whole country was growing at the 0 growth rate. What is the use of changing people places? Shouldn't matter. So you would expect C to remain 0 in the presence of these exchange terms. But actually, redistribution, any form of redistribution, actually allows one to benefit from favorable opportunities. That is, if you change people places, then some of them will be in places which accidentally grow faster. And so the population will grow because of that, and then will rediffuse and try to find other places where maybe in the future the population is going to grow faster. So it turns out that as soon as you introduce some redistribution, C becomes positive. So even if individually each city grows at a 0 growth rate, the fact of moving around allows the whole population to grow at a non-zero. And if you want, in the context of diversification, this is really, in the context of portfolio management, it's really a consequence of diversification. You're trying to explore possibilities that are locally favorable. And because of the exponential, this is going to allow you to grow. And therefore, this growth is going to be kind of anchored forever. Maybe there's a simple way to think of that in the language of pinning. Maybe the physicists will prefer that argument. So imagine that these pinning sites have, the pinning sites are the equivalent of eta. And so some eta are negative, some eta are positive, meaning that some impurities are attractive and others are repulsive. But of course, if you're trying to optimize your energy, you're going to pick the points where energy is locally negative, right? And so the process of optimization here will give rise to an overall negative energy of this object because it will have followed the most favorable path. And so if you think of that as population, so population moves from site to site, and it's going to gather points, if you want, by being at the right place at the right time. Yes?
I was just wondering if it's possible that C also can become smaller than 0, so that people might take the wrong decisions. And
on average, no.
On average, not possible.
Yeah, that's the point. That it's at long times it's always the favorable thing that wins, not the unfavorable, because the unfavorable will be killed anyway.
I would disagree, I think.
No, I mean this is mathematically correct and physically correct too. I mean, this is my argument here about pinning. The ground state of this polymer will have a negative energy.
For the polymer, I don't know.
But it's the same problem. So if you want, it's the same idea that because if you're staying on your lane, you'll alternatively see positive and negative growth rate. Mm-hmm. But if you're able to move around, then think of the think of human population
Yes,
in
that was what I was thinking of.
And just because, you know, some of them will have made the wrong choices and they disappear. But the ones that go, it's really the, if you want, the nonlinearity of the exponential. The ones that go to right places, they amplify the population so much because of the exponential that in the end they're going to win.
So is it like if I distribute 1,000 euros on random places, €1 each, and one of them grows a lot, then this can give me more than 1,000 euros, even if I lose the 999.
Yeah, it's this point that, you know, there's no, it's
but then movement is still, I can imagine movement can also be dysfunctional.
Well, here it's random.
Yeah. If it's random, I could agree. But
it's completely random. So you're moving around randomly. You're exploring randomly.
Yeah. Then I can agree.
Okay. But you'll see later maybe more of that, more of the same.
This doesn't seem random. It seems.
No. I mean, these things are supposed to be randomly distributed.
Okay.
That's the idea of the model. That these eta I, the eta R of T, these are pinning sites, and they are completely randomly distributed.
But the path doesn't seem, it seems more like a shortest path about that.
No, it's not the shortest path. The shortest path will go straight. So you have to, you know, it distorts. Every time you distort the path, you pay some energy. So the only reason you're doing this is because there's a good site here. And there's a kind of bounty that you want to grab here, and then there's another bounty here, and so on. So you're going out of your way to collect these bounties. And in the end, your total bounty point is going to be positive. It won't be zero. If you go straight, that is if J is 0, then it's going to be 0 because you're going to randomly sample positive bounties and negative bounties. But if you go out of your way exactly to get the bounties, then you're going to be, on average, winning. And the point here is that if you want, even if you have random walks, it is the random walkers that will have followed the right paths that are going to win. So in terms of human population, if you want, imagine that this is a kind of space-time diagram. And so each point here is a local event in space and time. And so there are positive events and negative events. Unfortunately, we know that. And so you have random walkers going there. And so what you're seeing here in this analogy is the path that was taken by the population that dominates at this point. It so happens that the population that will dominate here will have followed a specific path, which is that one.
Yeah.
And therefore, it's going to be very numerous because it's going to be the one that has
and
the
dysfunctional
the
types,
right,
they don't reach.
that you have made the right decision. You can think of that also as a kind of Darwinian selection in a sense. The ones that have been successful will be the ones that dominate the population.
Yeah.
So it's the same story.
Yeah.
But sometimes, what's interesting about this is that depending on the way you present it, it looks counterintuitive or intuitive. Yes, sorry.
Just one question. So the growth rate, it will go higher than 0, but will the concentration of at the same time increase? Or
let me come back to that.
Okay.
Yes.
Yeah.
So that's what I said here. The average spinning energy in the directed polymer is minus C. So if C is positive, the average spinning energy will be negative. Okay, so the other question was about inequalities. So first question, growth rate. Second question, asymptotic distribution of relative abundances. This is WI equals ZI over Z. And what you find in this model, which is pretty nice, I think, is that in a very generic way, again, you can play with all the subtleties of the model, but what you find is a Pareto tail, a parallel tail, with a non-universal exponent mu, which is a function of the ratio of this J's to sigma squared. So this function f, it depends on the complexity of the model, of course, but it's an increasing function of its variable j over sigma squared. So what does it mean? It means that if you increase j, if you increase redistribution, you increase mu, and therefore you lower inequalities. So yes, in this model, kind of intuitively, redistribution reduces inequalities. But conversely, if for a fixed exchange rate, you increase the variance of eta, that is, you have investors that have much better investing opportunities than others, or locally, instantaneously, they have huge investment opportunities, then of course you expect that to increase inequalities. So it's really this ratio j over sigma squared that matters. Dimensionally, j is 1 over square root, 1 over time, it's a ray, and sigma is 1 over square root of time, so it's sigma squared is also 1 over time. So j over sigma squared is an a-dimensional quantity. So parallel tail, and this exponent mu can become less than 1, that is, you can have concentration when j is small enough, or when sigma is large enough, when the variance of these investment opportunities or the fluctuations of growth rate is large enough, or if heterogeneities in MIs, this is the sigma describes the variance of the MIs themselves. If they're beyond some number, then you have concentration, even in the presence of redistribution. So that's the global, the generic properties.
This was random redistribution.
I'm sorry, just finishing. So the two generic results are positive growth rate as soon as you have redistribution, and concentration transition if redistribution is small enough, and conversely, if redistribution is large enough, then you lose this concentration problem.
Yeah.
Yes.
That was random redistribution, more or less.
This is random redistribution. Yeah. This is generic. Again, you can play, and I'm going to give you some examples. So let's be a little more specific about the type of models that we should consider, or we could consider for JIJ. So for example, you can think of JIJs as being non-zero between neighboring sites and zero elsewhere. So imagine that this is a very simplified model for people moving places. So each dot is a city, and each link here gives you the possibility to move from, I don't know, Utrecht to Amsterdam, but not to Rotterdam. Maybe Rotterdam is closer than Amsterdam. I don't know. No?
Roughly similar.
Roughly similar. Okay, anyway. So that would be Utrecht, Amsterdam, and Rotterdam. Anyway, so this is a very, this is not true. Of course, people can move much farther than that. Maybe in the Middle Ages, this is not such a bad model. So this is a two-dimensional lattice. Of course, one-dimensional would be a chain, and three-dimensional would be cubic lattice, for example. And what is funny here is that you find that low connectivity or low dimension favors wealth gluts and favors concentration. So what happens is that if you're in dimension 1 or 2, that is in weakly connected networks in a sense, because this guy never speaks to that one, and so on, then the result, again, which is not trivial, is that there's hypercondensation. That is, mu is actually going to 0. So you're always in the concentrated phase, but you're in the extreme concentrated phase where this exponent mu is very small. You remember mu is this guy, and mu equal 1 is the concentration threshold. So mu equal 0 is kind of the slowest decay you can think of. So it's hyper concentrated in the sense that only one guy has the whole wealth. And surprisingly, this is always what happens in D equal 1 or 2. there's no way to avoid concentration in this case. This whatever J is the rate at which you transfer, because in a sense you're going in circles in these low dimensional objects. Once you're here, the only place you can go is here or here in one dimension. And so you're going to go back to where you came from, essentially. And because of that, there's no way to avoid concentration. If the dimension of these lattices is greater than 2, then there is a non-trivial transition such that mu equal 1 at the transition, and for J less than J star, you're concentrated, and for J larger than J star, you're not concentrated. You can solve the model on trees, on these networks here have a lot of loops. A tree is a network without loops. And again, you find that there's a concentration transition when the number of neighbors is low enough. That is, if J is the same, you don't change J, but you change the number of neighbors. When the number of neighbors is large, you have no concentration. When the number of neighbors is low, you have concentration. So, the bottom line is that as soon as you hobble diffusion by low connectivity or by these loops that drive you back on your paths, on your previous paths, and not allow you to diffuse efficiently, then there's concentration. Again, this conclusion depends on, remember I said eta is no tails, no tail events. If there are tail events, this might change the thinking. Okay, so let me look at the model that we're going to study in details this afternoon, which is a case that you can think of as the Wealth tax, or in physics terms, it's a kind of mean field limit. So the Wealth tax is Jij is J0 over N. So it's the same for all I and J. And if you think about what this means, and we'll see that more clearly this afternoon, it means that everybody is taxed on its wealth with rate J0. So maybe think of 1% per year of your wealth is taxed. And it's redistributed uniformly among all the population. Okay. And in this case, what you find, we'll find this afternoon, is that mu is 1 plus something that's positive, J0 over sigma squared, 2 times J0 over sigma. And you see obviously that because it's 1 plus something positive, J0 here, the tax rate is positive, so, and sigma squared is positive, then mu is greater than 1, and so you have no concentration. So whatever the value of J0, even if it's very small, you have no concentration. So that's a very efficient way to disallow concentration. If you have this wealth tax, then whatever the value of sigma and J0, you'll always end up in the phase where there's no wealth condensation. Doesn't mean that it's not going to be unequal. And if I remind you, my chooses to go one way or another. Remember, this is the empirical value of mu for wealth in the US, say in the 2000s, 1.5. So it's above 1. So it's not true that the finite fraction of wealth is in the hand of few people back then. Now it's not clear anymore. I mean, actually, the recent numbers is that the 400 wealthiest Americans hold 50% of the wealth in the US. Anyway, so 1.5 is above 1, but it's still unequal. I mean, so you avoid condensation, but you remain in an unequal situation.
And for the long term, because if extreme situation, if a very high income earner spends all of his money, so very consumptively, or how would you call it? Which is not very sustainable for environmental purposes. If you compare that with someone that doesn't uses all his money or her money, and so accumulates wealth, you could argue that for the long term, you lose money for long-term investments, and it decreases growth. And with regard to sustainability, would it be bad also?
Okay, let me think about this. Maybe you can ask the same question a little later when I'm going to speak about something I think related to what you said.
But that's more of a question like, would it be better to have a wealth tax or a more progressive income tax, or
yeah, sure,
or a combination of it, but or differentiation between how
it depends on your objective.
What type of investment with regard to?
Yeah. Okay. So let me come back to that a little later. So you see this nice formula here, and when J0 is small compared to sigma squared, so if the tax rate is small, or if you remember that in the context of cities, J's is the probability of migration. So if migration is somewhat weak, then you see that you get to mu equal 1. So mu equal 1 in the context of this model is a natural limit. So the zip floor that we saw for cities or for firms, in the sense it's a natural case for this model because it's just a case where immigration effects are small. But I'm not saying that this is necessarily the right model for explaining the zip floor of cities, but actually it's very close to a famous paper by a French economist called Xavier Gabex, and he proposed essentially that model for cities. It's not framed exactly in that way, but it amounts to this. Okay, so what I propose is that maybe I go to the end of this and stop before 2 hours, because I think at this point it would be a bad place to stop, except if you prefer to have quick pause. So maybe, I mean, some of the questions before are going to be answered now. So I'm going to ask the question more precisely now. You remember I said the average growth rate is 0 when J is 0, and it's non-zero when J is non-zero. So the mere fact of moving people around creates opportunities for growth. And now I'm going to try to be more specific about the dependence of this growth rate on the immigration rate, the fusion rate. So again, J equals 0, I told you, if there's no possibility of moving around, then C is 0. And because I've said that before, but let me recall what it means in terms of path optimization. It means that if J is 0, the path here has to go straight. And so it's going to alternatively visit good sites and bad sites. And this is going to average to 0. But as soon as you allow this to move around, you're going to pick up the good bounties. So what is the shape of this growth rate as a function of J? Well, these are numerical simulations and a theory that I won't explain, but it's possible in some cases to actually compute these things exactly. But what you find is that as a function of J, look at this curve here, C increases and then decreases. And the reason is that if J is very, very large, so remember J has a unit of 1 over time. So J is a rate. It's the rate of changing places. So if J is greater than 1, it means that as soon as you arrive in a given city, you move elsewhere. And so you have no time to benefit from the fact that maybe this city was a nice place to live in and to have children and to grow, because you're already gone. So what it means, this maximum, is that in order to maximize the growth rate, you should stay a certain time when you've moved before moving elsewhere. If you don't move at all, then this is my argument that there's no growth. If you move too much, there's no growth either. But there's an optimum value for the growth rate. And so this can be framed into something that economists, or actually people interested in company growth or exploration exploitation. If you explore all the time, then you're not growing. You invented something, but instead of trying to monetize your invention or to make profit from it, you already do something else. But on the other hand, if in a company you never exploit, then you're also doomed to fail because someone else will climb the next trick. So that's called the exploration exploitation. So it's exactly what happens here. You should move, but not move too often. And that's the trick to make your growth as large as possible. And then if you're interested, I won't cover that in the hands-on because it becomes a little technical, but we have a paper in 2014 where this graph is taken from. Okay, so let me give you a highly stylized version of what I just said, and maybe it's related to your earlier question and we can discuss that. So I'm going to look at a case where I have only two sites, two types of individuals, if you want. So 1 and 2. So I repeat here my equation. I have dz1 dt equals phi z2 minus z1 here. Sorry, I've changed notations. Phi to be j, but it's the same idea. So there's part of z2 that goes into 1 and part of z1 that goes into 2. So there's this balance term, which is my immigration term of before. M1 z1 is the average growth rate of 1 with average growth m1. And then the fluctuating part, eta 1 z1. And the same thing so for z2. So of course, the sum of these two terms is 0 because it's not because you move people around that you're creating anything locally. So what was at 1 ends at 2, and what was at 2 ends at 1. So there's conservation of wealth, mass, if you want, at that level. But 2 grows with a different m2 and a different eta 2. Okay. So this is really a watered down version of this general model. Okay. But in a sense, it's the simplest model you can look at. So I have two entities. These could be cities, it could be individuals. They have different growth rates. The expectation of eta 1 is m1. Sorry, this is not consistent. It's now eta I have expectation 0, but what I mean is before taking the expectation values, they have different average growth rates. So for example, yes?
I understand we are trying to make a very simple model.
Yes.
But then we are just considering 2 cities. Maybe we can add a constant or an extra parameter to consider the inflow or outflow from other cities.
Yeah, sure. You could do that as well. I'm restricting to that case because it's already quite interesting. But of course, you can add these things. So imagine that, for example, these are 2 habitats for a given species. So the species, it could be a bird, I don't know, that can have 2 habitats. One is favorable, the other one is less favorable. And it can migrate maybe the north of an island and the south of an island to be in the spirit Darwin. The other example would be, let's think of Z1 being the private wealth. And on aggregate, the private wealth is invested in investments that have an average rate of return M1. And 2 is public money that has an average growth rate M2. You can, discuss whether M1 is greater than M2 or vice versa. Are individuals more efficient in the way they invest money for the growth of the economy or not? So a lot of people would argue that maybe M1 private money is smarter than M2, so maybe M1 is larger than M2. I don't know. Maybe you can argue otherwise. But certainly in the same spirit, the variance of eta 1 for private money is probably larger than the variance of sigma 2. Private individuals, they can invest in crazy projects. So this means that
But
Which is great. I'm sorry?
Public money as well.
Well, public money less so, because usually public money, you have committees that have to agree on something to be invested. Whereas private people, they can, you know, decide in 1 minute to invest in a crazy thing. Anyway, so I'm just giving stories here, but what's interesting is that you can solve the model for any combination of parameters. The third example is investing in stocks. That's the part of your portfolio invested in stocks, and that's the part invested in bonds. So again, maybe stocks have a higher return rate on average, but also higher fluctuations. Okay. And so phi, which is, as I said, J, is the way you transfer money from 1 to 2, or migration in the case of birds, wealth tax in the case of private versus public, or portfolio rebalancing in terms of stocks versus bonds. So here I'm just repeating my whole story, but in a very, very simple context of having two stuff, 1 and 2. And it turns out that you can actually solve this model. It's not trivial, it's interesting, but you can solve it analytically for any values of phi, sigma, M1 and 2. And the result is I think very nice because it's non-intuitive. It is that even when M1 is greater than 2, so you know, think of that again in my example of private money versus public money, then you know, liberals or people interested in making the state as small as possible, they would argue that individuals are smarter than the state in, you know, deciding what's good for the society or not for the society, the economy, and therefore we should tax as little as possible because M1 is greater. But actually, if you look at the average, the growth rate, the global growth rate, it's optimal to tax one a little bit and benefit from rare exceptional periods where the state was right. So it's the same argument again of, you know, transferring things from one place to another to diversify and be better on the long run. So this is a graph of the optimal tax rate in this model. Well, it's a highly stylistic model, right? But I think what's interesting about this simple model is that in some cases they give you non-intuitive results, and it's nice to think about this. So this is the difference between M1 and M2. So 0 means that they're the same. You know, other parameters in the system that are different, for example, the variance of eta 1 and eta 2. So when M1 is greater than M2, you're in that region, and M1 is less than M2, you're in that region. And so this is the optimal tax rate. You know, if you're interested in the global growth of the whole economy, that is of Z1 plus Z2. And what you find is that even if M1 is larger than M2, you see that the optimal growth tax rate should be positive. Then beyond some threshold, if M1 is really larger than M2, you should let individuals decide. But there's a region where the difference is not that great, where actually it's beneficial to tax. And on the other side, you might think of that as a communist dream. If you think that individuals know nothing and the state was better, then if M1 minus M2 is really very negative, then you should tax 100%. And then there's this taxing. So, you know, you can make whatever you want of that model, but I think it's quite interesting to see that there are two transitions, one where you should tax 100%, one where you should tax 0%, but these two transitions are not at 0. They're far away from 0. And there's a region here again where even if proponents of a nimble state are right, it could be still favorable to introduce some tax. In the context of polymers, there's also an interpretation, but maybe I don't want to go. Okay, so I've been a little faster because I've dropped the directed polymer part, which maybe it's a little too much. So let me just summarize and let's start there and maybe leave time for questions. So what I've shown or told you about is this very generic multiplicative growth and redistribution. And what you get is a Pareto tail with parameter that mu, with exponent mu that is parameter dependent. So there's no universality in this case. In physics, there's a lot of models where power laws have universal exponents. Here it's not the case. The exponent depends on the parameters of the model. But there's some universality, there's still some universality in some cases. For example, I've said that ZIF is a special case, which in a sense is attractive because as soon as one parameter is much smaller than the other, you can get to ZIF. I've argued that redistribution can prevent extreme concentration or can prevent pinning in the case of superconductors. But we've also seen that network topology is important. For example, if network topology is too open, is too close, sorry, is too restricted, like one-dimensional chains or too small number of neighbors, then you always have concentration, and no matter how much tax you, I shouldn't use tax. No matter how migration is effective, it's not enough to remove concentration. In the last part, I've shown you this non-intuitive optimal tax rate. Even if intuitively you would think that it's better to let the most efficient sites alone because they carry better growth opportunity, but it's still better to make people transit from one place to another. There are other redistribution channels that I haven't talked about. So for example, you can think not of wealth tax, but inheritance tax. So imagine that you have objects that grow multiplicatively, independently, like my very fast model here. So you have these guys growing. They don't exchange anything until they die. So there's a death rate. So this guy is growing for maybe, I don't know, years. And then with a Poisson rate, you kill the individual, or you make it disappear. And whatever wealth it had, you redistribute it among all surviving people.
Then so you weren't born then? Or?
I'm sorry?
And you won't be born again?
Yeah, you let newborn appear in order for the population not to shrink.
Yeah.
But yes, this is important, of course. And then you get something very similar to this model. In a sense, instead of having a permanent wealth tax, tax only people when they die, but the end result is more or less the same. You can avoid concentration thanks to that. And that's about all I wanted to say this morning. Again, barring the directed polymer on which I can come back if some people are interested. So if you want, we can stop here and ask questions. Sure.
You come from a physics background, if I'm wrong. When you study these superconductors, polymers, do they follow the mathematical models precisely, or because I ask this because we are trying to study socio-economic network systems here, and they are very random or not following any certain physics rule or mathematical rule. So, would you comment on it?
Well, I'm not 100% sure I understand your question, but let me say that this is really a model that comes from first principle. I mean, the physics of these directed objects is really described by what people call partition function, which is given by these objects. So for sure, this is a good model for equality. But I think that in the socio-economic context, the model is so broad at this level that I think it's also okay for a lot of actual phenomenon taking place in socio-economic context. Because here you see, as was asked all along the lectures, these JIJs are at this point not defined. So you can, put anything more specific that I've not described because I wanted to remain at a very generic level. But things that you would think important, you can always include them in the JIJs. You can also fiddle with things. For example, as I said, here there's no saturation effects. So we know that in the context of growth, wealth growth, it's not obvious to see where saturation would come from. But in terms of firm growth, maybe there's, as firms grow too large, there's a natural reason for them to have more difficulty growing, like management or economies of scale that become less.
Diseconomies of scale.
Diseconomies of scale. And in terms of cities, of course, as I said, I mean, at one point, you can't accommodate more people because there's no space anymore. So you would expect that all these saturation terms should be added to this equation. But what I wanted to show is that even within the context of this very, very simple equation, there's so much going on that one should be aware of what are the possibilities before adding more complication. Yes?
I was wondering, is there more work already on exploring different network technologies and how they affect the outcome?
Yes, there's a little bit of work, but I think it's still very much, there's a lot to be done still. So for example, if you have heterogeneous networks, that is networks where the degree of each node is different, then it's not clear what the distribution of wealth or distribution of size is in the end. Because in a sense, the mean field model that, again, we're going to study this afternoon, it tells you something about the fact that mu is larger if J0 is larger, and it means also that mu will be larger locally if the number of neighbors is larger. If you exchange with more people, there's less chance of you getting, maybe not. So for example, this is a main problem I have code up right now, trying to work on the case of heterogeneous degree distribution. Yes? Oh, sorry, there was a question behind.
In terms of the dynamics between the species, is it possible to study the dominancy of one species against the other with this type of equations? Because, for instance, with the wealth condensation model, everything is homogeneous. So all the indexes are running through agents that are kind of homogeneous, and they just exchange wealth. But if there are different type of species of any kind, is it possible to see this dominancy affects, for instance, the wealth or the quantity of any of the species starts growing, and then it's dominated by the growing of the other species?
So that's what I said here. I mean, you can, for example, you can easily extend these results to a case where species grow with different average growth rates. And then it's already quite interesting to see that even if, so you remember, I said, if there's no redistribution at all, then obviously the species that grow on average faster will be the dominant ones at long times. But already if you introduce this redistribution, this is not true anymore. If redistribution is strong enough, even if some species grow faster than others, then they won't dominate at long time, in the sense of Imperial index and condensation and so on. So that's quite interesting to see that you can in a sense regulate even these true heterogeneity, these true inequalities that exist at the level of individuals. So something else that you can add for describing heterogeneity is the question that was just answered, that if these GIJs have described heterogeneous degree distribution, then I think that something similar will happen, but it's yet to be described. So you can introduce, because the model is so vast, you can introduce whatever type of heterogeneity. The question is, as usual, to find a good balance between simplicity and solvability, and try to extract some message from what you're doing. Oh, you had a question?
Yeah, you had this example with low dimensionality,
right?
Where there was not enough dissipation
not enough spreading.
Not enough spreading, but would it be if you would allow for jumps in low dimensional systems? I can imagine you
yes, sure,
can get enough spreading.
Yeah, sure. If you in a sense, the way I'm drawing the graph and the way I'm putting connection is two different things.
Yeah.
So here I'm drawing a graph and I'm constraining my links to be local. If I constrain them to be local, but still not only nearest neighbor, but second nearest neighbor, it's not going to change the result. If I constrain them to be a jump to any distance with a finite variance, how the distance is not going to change. If now you introduce these Levy jumps, that is, you can have links that relate people very far away with some distribution that decays slowly now, then you're going to change it. And actually, if you have a jump distribution that doesn't depend on distance at all, then you're connecting everybody with everybody else, and then you're in the mean field, the so-called mean field.
And then you get
spreading, and then you get no condensation at all. So you can have, even if you draw your dots on a plane, you can have all the phenomenology between hypercondensation and no condensation.
I think that was related to your question. Network topology.
Right.
Test all kinds of crazy things.
You can, But again, so that's what I'm saying. You can invent any rule. The question is, you want the rules to be reasonable and plausible, and you also want to have a clear message that gets out, because otherwise the model is just too large.
But something like,
if you're running in all directions, you're not going to do anything interesting in the end, I think. Or else, if it's motivated by data, if you have real data and you can calibrate the model on data, then it's interesting.
Something hub and spoke like is something I would think of might be interesting. But kind of very big jumps between hubs and around the hub.
Yes, right. And this would be in ecology islands, intra-island and inter-island.
And for humans, some cities are connected. London is closer to New York than to, Newcastle sometimes.
I think there was one question from you.
I will get back to it during break.
Okay. You had a question.
Yes, I mean, often you hear that there's, in economic systems, the dynamic of the rich get richer precisely because they are already rich and can, for example, make daring investments or so on. So has anybody used that system? Maybe, with, for example, J's that make people receive what are already big or something. Has anyone tried to get that sort of dynamics out of this model?
So let me try to understand what you're saying. So here you already see that rich get richer because of this multiplicative effect. That's the basis of the model.
But that's, I mean, then if you only have this random growth, your initial model, then of course the rich will get richer, but they will eventually become poorer. So, so there's no sort of
because here the eta I mean, in most, sorry, I was trying to simplify, but in most of what I said, the eta I had means 0. So if you want, they were the same for everybody. But if you allow for this, what I call MI, then it's not true. MI, could have people who are, for whatever reason, have accumulated more wealth because of specific reasons that belong to them.
When you're smarter, you're more likely to get rich, sort of story, right? But
right.
But I think there's also in many interactions a tendency that not because you happen to be smarter, but because you are rich, even if you inherited it from your father, but you are not that smart, for example, whatever, that the fact that you already are rich have more likelihood to accumulate more, right? Because, for example, you can take direct investments or so. So I was wondering if someone has tried to capture that sort of dynamics where interactions with others are in the favor of the rich person by, for example, having your JIJs in some such way. I mean, I was wondering if someone used that model.
Yes. So indeed, you can mimic that in different ways. So for example, again, if you have an MI ZI, then if you're rich, you're getting richer anyway because of the ZI.
Let's just say that.
But you could add an exponent here. That means you make it faster than your wealth, growing super linearly. And the other possibility that you just said is having negative J's.
Sure, you can do it. I was just wondering if someone has used it.
So for example, this model that I'm going to talk about this afternoon, I mean that you're going to work on this afternoon, that is this one. You can think of that, although I've tried to avoid this, but you can think of that with J0 negative.
Yeah.
And it would go, I think, in your direction. And somehow that okay, we'll see that more clearly this afternoon, but it means that somehow money flows to the richest guys. So in this case, you cannot find a stationary state for the model, of course, because it completely explodes at long times. Everything condenses to, but you can be in a kind of non-stationary state and see what happens. And researchers in London around early Peters, I can give you the reference, have tried to interpret what's going on in the US right now exactly along what you said. That is with a negative J0, right? Trying to give a kind of systematic advantage to rich people towards which kind of money flows for structural reasons.
Yes, but also then probably like as a natural result in the end that will implode like a revolution, like the French Revolution or.
Sure, but then you have to add something in the model. I mean, the model doesn't have revolution.
That's the poison.
I'm sorry?
That's the poison you referred to earlier also.
The poison. Not poison.
You also mentioned the simpler model with only two MIs,
right.
MI1 and MI2, and then you showed that you basically are saying it's good if the liberals sometimes change, because then the effort, I don't know how to pronounce it exactly, but you showed that the outcome is better if there's a change between the MIs. And you mentioned something about liberals, so I was thinking it's good that politics changes sometimes from liberal to socialists and back again, because then then your end result is higher. Is that correct? That you
that
show it as well?
In a way, this would be having a time-dependent phi on top of that, because phi it increases when you have socialists and decreases when you have liberals. But I was saying something like slightly different, which was that even if liberals are right in the sense that individuals are better at spotting growth opportunities than the state, then you should still tax them for the benefit of the whole economy, which I think is really non-intuitive. And it's again the same question as the one that we discussed from.
It's a very little risk mitigation, so that the little bit that stacks that perhaps will be invested publicly in something that will really boom very much, and as a result also benefit in the end.
Exactly, it's diversification 101. In fact, you should not put all your eggs in the same basket. And if you have someone else, in this case, I mean, of course, we're assuming that eta1 and eta2 are not perfectly correlated. Here, actually, we're assuming that they are completely uncorrelated. But as soon as they're not completely correlated, then it means that the decisions made by individuals and by the state are going to be different, and therefore we can count on this to be beneficial on the long run.
And it's same the other way around with communism. If you don't have individual opportunity,
exactly,
and of course the state will also make wrong decisions.
Exactly.
They're not,
Yes.
So the optimum is a well balanced
taxation
system.
Yeah, and so when I started this project, my initial idea was that it could be 100% here and 0% here, and I didn't. I mean, what's nice about this model is that it's simple enough that you can really write down all the equations, but also that the final result is not obvious at all. Yes.
In this model, you did not include, let's say, subsidies to the rich or negative taxation in the model on this one. So you only have, let's say, movement or from private to public in this model? Also vice versa.
Actually, I've simplified it in the paper. I have two files. So there's here it's really you tax from the public, but you also redistribute to the public with the same rate.
So both public and private.
Yes. So you see phi Z1 minus Z2, Z2 minus Z1. So it's completely symmetric. You tax the private and you redistribute to the private. But of course, not the same amount. Depending on whether Z1 and Z2 is larger, you're going to have net flow from public to private, but it depends on time. So microscopically, this model means you're taxing and redistributing. But actually, in the paper, there's a phi for tax and phi prime or psi for redistribution, and you can also look at the dependence on these different things. Yes.
I had a similar question regarding to additions to this model, whether you could also model debt accumulation as well as wealth accumulation, because debt is kind of interesting to me in this, because wealth is distributed a little bit, but debt, at least in the Netherlands, is not. Like if you are an individual in debt, it grows exponentially, but it's not redistributed.
I think you know.
Well, in a way, also debt is redistributed, because if that person goes bankrupt within the banking system, otherwise,
I suppose so.
Okay, the model should be modified because here it's really written in terms of positive ones.
Right.
And so,
but that is not included at all.
It could be interesting to think about extending this to negative wealth.
Right. So then maybe also you wouldn't see this if you pin wealth at 0. So if you go back to the original simplest equation, you might not see this effect of redistribution causing growth.
So actually, if you look at this thing for the US, it actually starts negative.
Right.
The poorest people are in negative. Well, so it does a little bit like this, and then actually what happens now in the US, as I said, between 2005 and now, what has changed is that if you look at this Gini, Lawrence curve for the US, it's really very striking. It's a kind of regular graph like this, and then it reaches this point, and then it starts. So there's really something that happened which is non-trivial. That is, there's really condensation in the US right now. Right?
Just as an extra comment, so Martin Scheffer wrote a really great paper about that situation also, where indeed if you see, I don't know if you know his work, there was an earlier question about French Revolution, but he also looked at all the revolutions across history, and that you see that kind of moment of revolution. So maybe that's what's going on in the US. I don't know.